Hey everybody, in this video we're going to be practicing related rates. Specifically, we're going to be doing all the related rate problems that are pertaining to volume. If you're looking for other related rates, there are other videos on this same playlist that deal with things like area, Pythagorean theorem, and trigonometric ratios. So you can look at those other videos for those types of problems. If you want to follow along with this video, the link to the companion worksheet is in the description below. So let's get started. So what we have here is we have a picture of a water trough. It's triangular in shape, and we're filling it with water. And water is flowing in at the rate of 2.5 cubic feet per minute. And the question is, how fast is the water level rising? One thing that people get incorrect about this is the water trough itself isn't what's changing. It's the water that's changing. And so we have to think of, well, what is the volume of this water? Well, the volume would just be the area of the base, which is a triangle, times the height. So that would be the area formula. The base times the height. Now, what people have a hard time visualizing is that this is a triangular prism on its side, and the height is a constant. The height is a constant of 15. And so the area of the base, well, that's a triangle, so that's 1/2 base times height times 15. Now, in a problem like this, as the water level rises, obviously the volume is changing, so that's going to remain a variable. As the water level goes up, the base is going to get longer, so the base will remain a variable, and so will the height. Now, one method that I often recommend to my students to make this easier is to say, well, wait a minute. The base and the height are in a certain relationship, and if you can discern that, we can remove one of these variables. So let's look at that. For this entire trough, let's look at that. The entire height would be 3 feet. So let me draw this cross section over here. The entire height would be 3, and from here to here, it would be 2, because the entire trough is 4 feet across, but we're only looking at half of it. Now, the water follows a similar proportion. This is the height, and this is half of the base, because the entire base would be all the way across the triangle. Now, what we have here is we have a proportion. And so we can write this proportion as 2/3 equals 1/2 the base over the height. And we can say that because these two triangles are similar triangles. They're not congruent triangles, the sides aren't the same length, but because their angles are the same, all their sides are in the same proportion. Now the question is, well, what do we want to solve for? What do we want to eliminate? Well, if we look at the question, it asks, how fast is the water level rising? So we want to know how fast is this variable changing, which means we don't care about the base. So what we're going to do is we're going to get rid of this. We're going to substitute that out for another expression with h in it. So over here, with my proportion, what we want to do is we want to get b by itself. So the first thing we do is we multiply by h. So we have 2/3 h equals 1/2 b. And then we multiply by 2. So 4/3 h equals b. So now that b equals 4/3 h, we can make that replacement over here. So 15 and 2. So we can combine those two coefficients. In place of b, we have 4/3 h times h. And so now we can combine these two fractions. 15 and 3 will cancel, leaving 5 on the top. 4 and 2 will cancel, leaving 2. So that means we have 10h squared. So now what we want is we want to talk about the rates of change. So here is where we find our derivative. So we find the derivative with respect to time. So dv dt equals 20h dh dt. And so at this point, we now say, all right, well, what is the change in volume? And they tell us that's how fast the water is being poured in. So that's 2.5 cubic feet per minute. Now, what is the height? Now, the height is a variable, but at this moment in time, the height is 2. And so we want dH dt. So that's 2.5 equals 40 dH dt. So to get dH dt by itself, we'll divide 2.5 by 40. And we get 0.00625 is what dH dt equals. And that actually simplifies to a nice fraction of 1/16 dH dt. And because this is a rate, and because we have units, we want to include the unit here. And so height is measured in feet. And time here is measured in minutes. So so the height at that time is rising at a rate of 1/16 of a foot per minute. Okay, let's look at the next one. Now with the next one, we have the volume of a cube, and it's decreasing at the rate of 10 cubic inches per minute. Now how fast is the total surface area decreasing when the surface area is 60 square inches? Now what we have here is two different quantities. We have the volume of a cube and the surface area of a cube. Now those are two different formulas. The volume of a cube is equal to the edge of a cube cubed. And the surface area is equal to 6 times the edge squared. Because there are 6 different faces, each of them in the shape of a square on a cube. So, well, we know this rate, and we want to know how fast the total surface area is changing. So what we may have to do is we may have to work with both of these. Now, so the rates of these is going to be dV dt equals 3e squared times dE dt. So here's one formula. And then over here, we need the change in the surface area, dSA over dt equals 12e dE dt. So the only thing we can plug in right now is 10, and that's the rate for dV dt. Now what about the edge? Well, we could figure that out because we know that the surface area is 60 square inches. So at that moment, we should be able to figure out what is the length of the edge. So when we do that, all we have to do is, off to the side, we'll say that surface area equals 60 equals 6e squared. So if we divide by 6, we get 10 equals e squared. So square root of 10 is the length of the edge. So we can plug that in. So square root of 10 squared times dE dt. All right, so now we've got an equation where there's only one unknown. That's good, that works for us. So if we simplify the left side, if we square root of 10, that's just 10. And so 3 times 10 is 30, so 10 equals 30 dE dt. And so that means dE dt, when we divide by 30, is going to equal 1/3 of an inch per minute. However, we're not asking how fast the edge is changing. We're asking how fast is the total surface area changing. Now actually I forgot one little detail that's kind of important. It says that the volume of a cube is decreasing. So that means when I put 10 in for dV dt, it should be a negative. Now that doesn't change much in the way of our calculation except for the fact that the cube is decreasing. So that means the edge is decreasing. The edge is decreasing at the rate of 1/3 of an inch per minute. Now we can plug that number in up here because at the same moment in time that the volume is changing, so is the surface area. So, but we also know that the edge at this time is still square root of 10, because that's the moment in time we're talking about. So at this moment, the surface area is 60, and the edge is square root of 10. And so now we plug in negative 1/3. And so that's going to be negative 4 square root of 10 as an exact answer. And if we make an approximate answer, that's going to be approximately negative 12.649 square feet per minute. Because again, we're talking about the change in surface area, and area is measured in square feet, not in linear feet. Actually, no, not feet. My apologies. That is inches squared per minute. All right, on to the next one. So here we have a cone, and it's being filled with water. So this has a similar feel to the first one where we had a trough, and that is where we have a container, and then inside that container we have what we're actually talking about. So inside of that we have the actual water. Now water is growing. It's being filled with water at the rate of 2 cubic inches per second. Now we know that the big cone has a height of 10 inches. So 10 inches, and has a radius of 2. So from here has 2 inches. Now the cone that the water is shaped in, that's changing. So we'll call this R, and we'll call this H, because those are both variables, and those are going to change over time. So now our formula for the volume of a cone is 1/3 pi r squared h. Now, similar to the trough problem, what we want to do is we want to ask, well, we have two different variables. Both r and h are changing, but we can substitute one for the other so that we have just one variable here on the right-hand side instead of two. So what we look at is we ask, how fast is the surface of the water rising when the depth is 6 inches? So that means we're asking, how fast is h changing? So we want dh dt, which means r doesn't really matter for us. So we can substitute r out. So the ratio of r to h is equal to 2/10. So we'll solve for r, and so r equals 2/10 times h, or more simply, 1/5 h. And so that is what we can substitute up here. So volume equals 1/3 pi. Now remember, r is being squared, so that means this whole quantity, 1/5 h, is also being squared. A lot of people forget to do that. And so when we square it, we get 1/25 h squared times h. Now we can combine these coefficients. So we have 1/75 pi times h cubed. And so now we have a volume formula with just one other variable on the right-hand side. So now we can find the derivative with respect to time. So dv dt equals 1/75 pi times 3h squared times dh dt. And we can simplify this by combining the 1/75 and the 3. So we have 1/25 pi times h squared times dh dt. Now what's being asked of us? How fast is h rising? So that means dh dt is what we want to know. So that means we have to plug in a value for dv dt. That's the change in volume. And so that is 2 cubic inches per second. So that's 2. And h, they tell us, is 6 inches. So 6 squared equals dh dt. So now all we have to do is algebraically get dh dt by itself. So we'll multiply 25. So we have 50 equals 36 pi times dH dt. And then we can divide by that whole quantity, 36 pi. 50 divided by 36 pi equals dH dt. And that is an exact rate, but if you want to find the approximate, that's going to be approximately 0.442. And the unit here is inches per second. That is the rate at which the water level for this cone is rising. All right, let's look at the next problem. Here we're talking about a spherical snowball. And so it's saying the radius is decreasing at this rate when the radius is that amount. And so we want to know how fast is the volume decreasing. So we're talking about radius and we're talking about volume of a sphere. So that means that our volume formula is the volume formula for a sphere, 4/3 pi r cubed. Now, unlike the last one, there's only one variable, so we don't have to make any substitutions. All we have to do is find the derivative with respect to time. So dv dt equals 4/3 pi times 3r squared dr dt. And we'll simplify by multiplying the 4/3 and the 3. So that means we end up with 4 pi r squared dr dt. So it's asking how fast is the volume decreasing at that time. So that means we want to know what dv dt is. So that means we need to find out, well, we need a value for r. That's the moment in time what the radius is, which is 20 inches. Pi times 20 squared. And the radius is decreasing at 0.4 inches per hour. Remember, it's decreasing, so that means that rate is a negative. And so we'll multiply those together. So 4 pi times 400 times negative 0.4, and we get an approximate answer of negative 2010.620. And the unit here is cubic inches cubed per hour. That is our unit for how fast the volume of this sphere is changing at that time. Remember, it doesn't stay that way. It changes as the radius changes. All right, for our last problem, here we have an oil slick on the ocean, and it is expanding. At least the radius is by 0.1 feet per minute, and the thickness is 0.02 feet. So if you can imagine a circular oil slick, and it has the tiniest of thickness, and that is 0.02 feet. Now currently, the radius is 150 feet, but it's growing. Now it tells us that the volume of this oil slick remains constant. It's not changing. So how fast is the thickness of the oil slick? Well, that means that the oil slick thickness is getting smaller. So that means it's an actual variable. So what we have here is we've got a formula for the volume of a cylinder, because that's what this shape is. It's a very flat cylinder with a very small height, but it's still, that's what the shape is. And so that's volume equals pi r squared times h. Now, important thing to note is that they tell us that the volume is a constant. Now, we could go about and calculate what the volume is, but actually for our purposes, it's not necessary. The reason is, when we take this derivative, if the volume is constant, that means its derivative is 0. So we can leave it like that. Now, the thing to remember here is, here we've got two different variables that are being multiplied. So that means we have to use product rule. So if I take the derivative of r squared, that's 2r dr dt. And we leave h alone. And then we leave r squared alone, and then take the derivative of h. So we need to plug in values for r and h and for dr dt. So that should leave dh dt by itself. So it says when the radius is 150 feet. So that number is what goes in for r. And the radius is expanding by 0.1 feet per minute. So 0.1 is what dr dt is. And at that moment, the height is 0.02. So all of that represents this first term right here. Then we have pi for the second term, and then r squared. So that's 150 squared times dr dt. Sorry, dh dt. So now at this point, now we have to get dh dt by itself. So one thing we can do to make this a little bit easier on ourselves is to note that, hey, we've got a pi in both of these. We can factor that out. And so we have 2 times 150 times 0.1. And that will be a nice whole number of 30. Whoops, forgot the 0.2 out front. Oh well, we'll get that next time. And then we have 150 squared. 50 squared, which is 22,530 times dh dt. Now, why do we factor out pi? Because we can divide both sides by pi, and since the other side has a 0, then who cares? And that makes all our numbers just that much nicer. So let's remember 30 times 0.2, that should be 6 plus 22,530 times dh dt. So all we have to do is subtract the 6 and then divide by 22,530 to get the dh dt by itself. So our change in height is -6 over 22,530. That's an exact answer, or as an approximate, that's going to be -2.663 times 10 to the -4th. And the units of this are feet per, and our time unit is minute. So that is how much our oil slick flattens out every minute, almost non-perceptible. Thanks everyone for watching. If you liked the video, please give it a thumbs up. For more videos like this, click the subscribe button. If you're a teacher and you like this, consider sharing this with your students. If you're a student and you like this, consider sharing this with your classmates. If you have suggestions or problems that you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching, and remember, the only way to understand something is to do it.